Hey, so this is lab 2. This is motion of a falling object, and I'm Will Wood. The purpose of this lab was to study an object that was initial zero velocity and then fell. Okay, so the physics principles here are the momentum principle. So we have velocity and position update using a net force, and then the force of drag, which is in our case proportional to velocity squared. We use these because we can model the behavior of a falling object in the y direction with the momentum principle, and we have force of gravity and the force of drag. And then we also saw basically what we did was we observed behavior of a falling object, and then we created a computational model to predict behavior, and then we created a better one. And we saw that the one using accounting for drag was better than the one that just used force of gravity. Here is the video. It's me dropping and an object falling, and it was paper towel roll. The experiment, or it was a paper towel crumpled up, and the system is the paper towel, and the surroundings is everything else, like me, the air, gravity, everything. And then here was what we observed. This is position versus time of our paper towel from GlowScript. And then here is one model to model it. We can see that we have initial conditions of mass 1, position 2.275 meters in the air, velocity 0 initial, and then some time steps that we got from our video, and then force of gravity. Basically, we just updated the position and velocity of the ball based off the force of gravity using the momentum principle, and then graphed it. And here's a better model using drag. Same initial conditions, except now when we did net force, we took in the force of drag, which we said was the magnitude of velocity squared times b, which is our drag constant, which is 1. And then we set velocity and position according to this. Here on the left is from our original model, where we saw that the ball ended up going too far, and there was only force of gravity, which is our orange arrow. And then on the right is our blue arrow pointing up is force of drag, going against the orange arrow going down, which is force of gravity, where we saw a much better model. And we can see this from this graph, where we have yellow is our better model, accounting for drag and gravity. Red is just gravity, and blue is our observed. We can see that our drag and gravity one matched our real data much better. Some sources of error for this lab could be GlowScript. Maybe not the best way to track our position. There was some horizontal movement, so we're not accounting for anything on the x-axis in this experiment. And also that, yeah, I mean, that's a big one. Okay. So what if the ball was thrown down instead of just dropped? So the way to model this would just to start our ball from a velocity, from some velocity, right, that is not 0. And we did that on this bottom right graph here. And what we saw is that our terminal velocity is actually the same as when we just stopped it. It's about 3.14 meters per second. And the reason for this is because when we throw a ball down, our velocity squared is higher because our velocity is higher. So we actually have a higher drag. So they both end up meeting the force of gravity towards the end. And what does this mean? In terms of which one had a terminal velocity, one with the terminal velocity was the one accounting for drag. And this means that the force of the drag was equal in magnitude, opposite direction of force of gravity, which is why you see no acceleration, which would be a constant velocity towards the end. So that is our terminal velocity. So thank you. That was a lab. We saw that the model accounting for drag was much better than the one that just accounted for velocity. And we modeled a falling object.